Great, so thank you very much. So interface latency is defined as the time between an input to a system and the system's response to that input. And we can see it in this example here. As the user drags the icon around, it lags behind. And we saw it in some of the examples from previous speakers as well. As they rotated stuff, there was a lag. And that's inherent to any system. You have sensors that have to be read. You have many layers of software that have to process it, ranging from the driver all the way up to the application level. And you finally have to wait for the display to update. And despite the march of Moore's law, there's still noticeable latency in all commercial devices. At best, the time difference between a tap and a response to the tap is down to about 33 milliseconds. In many cases, it's much, much higher, as high as 200. And humans can perceive down to 5. So it's clear we still have a ways to go to remove this impact on the user experience. But in order to do something about latency, you have to be able to measure it well. And it's not something that you can easily do just by eye. If I asked most people in here what the latency was of their phone, you probably couldn't tell me, right, off the top of your head. Now, there is equipment to do this. This is one example here of a commercial system from OptoFidelity. And these things are great. They're really flexible. They can measure all sorts of things. The problem is they tend to be priced in the "a sales representative will contact you" range, which means they're not particularly accessible for most people who want to be able to use them. There's many options for doing it yourself. The simplest is to simply observe it directly with a camera. So here's me tapping a screen, and that's not so useful. So what we do need is a high-speed camera in order to have a sense of what's actually going on. So let's look at this again at 960 frames a second, which is about 3% of normal speed. And I'm going to tap the screen, and eventually, after I tap it, the screen is going to respond. So we'll just wait for it, there it goes. So what you just do is you count the frames, and then you know what the delay is. The problem with this is that it's hard to know when the tap actually occurs, right? What's your 0 point for doing the timing? And it's labor intensive, both to do the tapping and to do the analysis. And just as an aside, this video gives us a sense of some of the complexities involved in measuring latency. We noticed how the screen refreshed from one side to the other, right? It wasn't that immediate white flash that we saw at the real time. And that's because we're picking up the screen as it redraws line by line from one side to the other. So if you're measuring the latency and you measure it at the left side versus at the right side, you're going to get different numbers for exactly the same interaction, right? So these are the sorts of subtleties that we have to start thinking about. Now you can try and simplify things a little bit in terms of figuring out when an impact occurs. And various projects have done that. This is one example that just came out a month or so ago from Google. It's something called WALT. And what they've done is they've put an accelerometer onto a pen to be able to measure that moment of impact with great accuracy. And we had some similar ideas initially when we were thinking about measuring latency. That's actually where the name Latency Hammer comes from, was we envisioned this kind of cartoon mallet that you would hit against a screen and it would give you a latency reading. But the problem is that if you're trying to have someone pushing a pen against something, you can't automate it because you're still having a human in the loop. The other option that you can do without having to build much in the ways of equipment is measuring dragging latency by simply sticking a ruler on your screen. And since everyone got a ruler in their conference bag, you guys could do this right now if you wanted to. You just have to measure it and see what the displacement is between the ink and the pen and calculate it from there. Now, this isn't particularly accurate, though, because if you're moving by hand, there's going to be variations in the speed that you're moving at, and that reflects in the calculations as well. So at Tactual Labs, which is a startup where myself and most of my co-authors work, we're working on extremely low latency touch systems. It's a shameless plug, by the way. And one of the things we spend a lot of time doing is investigating the latency of existing devices. And when we started doing some of these manual methods for this analysis, we found that we'd get results that were all over the place, even for the same device. And to just give a sense of what some of this data looked like, let's take a look at a plot that has latency on the x-axis and what I've labeled trial on the y-axis. And to get a sense of what that means, here's some data. Each point is one measurement. The first measurement, so the first trials are at the bottom, and then as we go up, it's later and later trials until we get to the last measurement we took at the top. So this doesn't look so bad, right? It's all grouped together, this nice chunk here, kind of in the low 90s. And if this was all we had, then there wouldn't be much of a problem. But as you can guess by this large amount of white space that's sitting there on the right side of the chart, there's probably some more data that I haven't shown yet. And sure enough, it looks like this. So this data set, it's 500 measurements, and this is with a Latency Hammer, by the way, not by hand, because we would have gone slightly crazy taking 500 measurements by hand. And what we're seeing here is that over time, as we get to the last third of our measurements, we're seeing much slower performance. And to be clear, these are intermixed. So we'd see a measurement of 90 milliseconds, followed by one of 130, followed again by 90 milliseconds. And what's going on is that a phone is a very complex device running a real operating system with lots of real-world considerations. And what happened was the phone started to overheat from the testing we were doing, and the system throttled down CPU cores so that it wouldn't get too hot. All of a sudden, the performance gets worse. If we let it cool off, we'd get back to the constant performance. So you have to start taking into account, if we have these sorts of variations going on, we need a really large data set. If we just had taken a few measurements, we wouldn't have seen this part of the data. So the moral is that latency is rarely a single number. That's convenient to be able to say, oh, my phone has 90 milliseconds of latency, but that's not the reality of how most devices tend to act. Instead, they tend to be a range. And to evaluate a range, you need to be able to take a large number of measurements. Now, the expensive commercial systems can do that, and there are many research systems that have tried to do large numbers of measurements as well. One example from last year's WIST from Cassier et al. Is the lag meter. And what this does is takes an optical mouse, puts it on the screen, and then moves a pattern around on the screen. This fools the mouse into thinking that it's actually moving on a table, and since you know when you move the pattern, you know when the cursor moves, you can calculate the latency. So that's great, you can do a lot of measurements, but that doesn't work on a touchscreen device, which is what we're particularly interested in at Tactual, certainly given the general trends of the marketplace today. So when we sat and looked at a lot of the existing work, they all had positives and negatives, but none of them had the exact set of requirements that we wanted to be able to easily evaluate touchscreen devices. So the goals that we wanted were something that was precise and accurate. It had to be able to measure a wide range, ideally down to the 1 millisecond range associated with the highest speed research prototypes, all the way up to 200 or more for commercial devices. It had to be cheap and easy to build, because otherwise we'd just go out and buy one of the really expensive systems. We want to be able to measure a wide range of form factors. We don't want to make any hardware changes to the devices that we're measuring. And most importantly, we want it to have automatic operation so that we can get these really big data sets. So this is what we built. This is the Latency Hammer. And you place a device you want to measure onto the hammer, and it's running one similar application to what we saw before that lights up when you touch it. You place the measurement head onto the device, you hit go, and the Latency Hammer will plug away and do as many readings as you want of tap latency. Now, the key to building something like this, if we want to make it cheap and we want to make it easy to build and really precise, that means that a mechanical motion is out. We can't move a stylus up and down because it's really hard to build something very cheap and very easily that's also incredibly precise as a mechanical device. So we need to get rid of that and replace it instead with an electronic switch. This means that we have a measurement head that stays in the same place all the time on the device, and the switch turns the touch on and off. The key to doing that is to think about how a capacitive touchscreen works. So there's a charge that's projected onto the surface of this phone. Electrons are sitting there, essentially. And when you touch it, some of those electrons are going to move into you because you're filled with water and have surface area, and that's going to change the capacitance on the top of the screen. The sensor then says, okay, here's a touch. Now, because we're talking about moving charges around, I don't have to touch the screen directly. I can touch the screen via something conductive. So here I've placed a chunk of brass on the screen, and I can still touch it, and it still triggers a touch. This is the same idea as a capacitive stylus, and it's the same idea for those of you who don't live in California of capacitive touchscreen gloves that have the conductive fabric woven into the fingertips for use during winter. Now notice that the contact by itself, when it's just sitting there, doesn't trigger a touch. It's only when it's connected to me. So because we're just having it connected to me, I could also connect it via a wire. So here's me holding a wire and tapping it, and it still works. So this isn't all that useful on its own because it's still me sitting there tapping it with a wire. But what we can do is use something else to change the charge that's on the screen. If we have something else that'll dissipate electrons into the environment, that'll also trigger a touch. So this is not actually part of the Latency Hammer, but it illustrates the principle. And we've hooked that wire up to this, which is a heat sink. Now, we're not using it to dissipate thermal energy. We're using it as a bunch of conductive surface area, as a way to dissipate electrons out into the environmental ground. So I've connected this to an official scientific plastic poking stick, which is not conductive. And what I'm going to do is just tap it to the contact, and we see that that triggers a touch. So that's the basic idea of the hammer. All we need to do is replace the poking stick with a switch, and we have something that can actuate the touch. This is the basic block diagram. So we have the brass contact sitting on the device, and we have the heat sink acting as an electron sink to connect to the environmental ground. And here's the switch that's replacing the plastic poking stick. Finally, on the other side, we have a photodiode, which is reading the response from the screen, and we have a microcontroller that's managing the whole operation, and it's based on an Arduino Due platform. Here's a picture of the underside of the measurement head. So we have the brass contact there, and we have the photodiode on that side. If we flip it over and take the cover off, this is what the inside looks like. There's the connection to the photodiode, and on this side is the switch. Now, we're using a mechanical relay as our switch because the change in capacitance needed to trigger a touch on a screen is incredibly low. It's in the femtofarad range. And a lot of, in fact, almost all solid-state switches leak just a little bit of current through them even when they're turned off. What that means is when we built prototype measurement heads with a whole variety of solid-state switches, we'd find that they would still create a touch event even when the switch was turned off, which of course is useless for what we're trying to do. So a mechanical relay, because it's physically separate contacts inside of it, doesn't have that same sort of leakage issues. Now, a relay is slower than a solid-state switch by orders of magnitude. It takes milliseconds to turn on rather than nanoseconds. But that's fine because we use a double pole relay, which means we get a signal back from the relay when it's actually closed. So we know the exact instant where the touch really occurs, and we use that for our timing. We are working towards a solid-state version, and we have some promising prototypes since a mechanical relay, while it does work just great, is a little bit inelegant, and it doesn't scale up if we're wanting to have multiple contacts very easily. Okay, so that's what the hardware looks like to us. Let's see what the hardware looks like if you're a capacitive touchscreen. One of the nice things about working at Tactual is that we're building our own touch sensors, so we have very easy access to raw data coming off the capacitive sensor. So this is a heat map of what the capacitive sensor sees, and the blue is the surface of the screen, and the higher any given coordinate is, the more signal we see. Right now, nothing is touching it, so we're not seeing much in the way of a signal. So now if I touch this with my finger, we see a spike that looks like this. So this red at the top means we've crossed the threshold, and this would be detected as a touch event. So I'm going to take my finger off, and I'm going to put the measurement head onto the screen. Now the measurement head is not trying to create a touch right now. We still have a spike, and this shows just how sensitive the screens are in terms of picking up metal objects that are placed onto them. But it's a low enough spike that it doesn't trigger a touch event. If I now go and turn the relay on, we get this, which is a spike that looks exactly like a finger. So as far as the screen is concerned, the measurement head is identical to a human touching it. So that's the hardware side of things. Let's take a look at the software. So the host software that's running on the controlling PC creates logs of all the raw data, but it also gives you a visualization that looks like this. So what you're seeing here, it's the same visualization with a little bit more data that we saw at the very beginning. And this time what was labeled trial is now labeled series. And that's because the Latency Hammer runs series of 10 measurements. So these points here correspond to the first 10 measurements that were taken. These ones correspond to the second 10, and so on. So we've done 25 series, or a total of 250 measurements here. What we see in terms of the distribution is this spacing of 16.7 milliseconds between these two big clusters of measurements. And the reason we see that is because a screen redraws itself only so often. At 60 hertz, which is the most common speed available today, that's 1/60th of a second, or 16.7 milliseconds. So even if a device is ready to present information to the user, if the screen isn't ready to redraw, it can't show up. So we tend to see these quantization effects that occur chunked at these 16.7 frame boundaries. So that's how the Latency Hammer works. The next thing I want to talk about is how we know that it works. And to do that, I want to first start talking about another piece of equipment that we built. And it's this. It's called the phone examiner, which we also call the phony. And it's a sheet of paper that I drew on with a marker. And what you do is you put your phone onto the sheet of paper, and then you read the number off it. And it's really precise. It has 5 decimal places of accuracy. That's much better than the latency hammer can do, right? Does anyone trust this? Would you use this in your research? No, of course not. It's a sheet of paper that I drew on with a marker, right? It's really easy to make a piece of test equipment. I did this in like 30 seconds. What's hard is to make test equipment that actually measures reality, right? That's the difficult part. And convincing yourself that you've measured reality correctly. So the validation that we did was a whole range of different steps. And by the way, this is about a third of the paper that I can't go through in detail now, so I'd encourage you, if you're interested, to take a look for more on each of these different steps that we did. We broke down and looked at the overhead associated with a variety of different subcomponents of the measurement process. We went and intentionally added delay into our application that lit up with a white touch, and then tried to measure that to make sure we were able to pick up our newly added delay. We built external hardware. We built a delay box, which rather than having an unpredictable latency performance like a phone does, was a very simple oscillator circuit that would always, once we set it to a given latency, would always have the same delay. We could then measure that with both an oscilloscope and the hammer and compare the results. We also did an optical analysis to provide a fully external way of examining it. And to do that, we built something called the direct optical hammer, which had a stylus that was able to draw up onto the screen, and a switch that could be calibrated to within a fraction of a millimeter to turn on at the exact moment that the stylus would hit the screen. That switch illuminated an LED, which let us, from a high-speed video, know when the stylus hit and do that analysis. Based on all of these, we found that we had something in the ballpark of a 1% error range that we were extremely happy with. But even better than that, looking at the results from the external delay box, which we think is the most accurate way of examining the hammer, our error tended to be in about 0.25%. So we were quite happy with what we were seeing. So just to conclude, I'd like to go back to our design goals and see how we did in each of these. The first is precision and accuracy. So we do end up with approximately 1%, which is just great. Our range can go everywhere from 1 millisecond to 200 milliseconds or more. You can build it for about $100, including the cost of the microcontroller. You can measure anything from a smartwatch all the way up to a whiteboard. You don't need any hardware changes. Custom applications like our white touch application work best, but you can often use a button highlight that lights up when you tap it. Will usually be sensitive enough as well. And you can easily do thousands of unattended measurements. Finally, we're planning on open sourcing the design in the near future, and we're hoping to work towards building a community to have both tools and as well standards so that we know what sort of thermal conditions, where on the screen you're measuring, all those things that make it possible to compare devices to each other. So if you'd like to have some information about that, you can sign up here. We'll let you know when we're actually launching the project. Finally, just like to thank all my wonderful colleagues at both the University of Toronto and at Tactual Labs, and open things up to questions. Thanks very much.
Shuming Jai Google. What you measured is a very good baseline. Do you also think that may differ from the actual human touch with its variance, both the biomechanically, but also, as you said earlier, the application situation may actually cause additional variance? So is the baseline upper bound or lower bound, or is there any variance from the actual
sorry, can I speak to the mic?
experience?
So I think, in terms of the response to a human, based on what we've looked at the data from the capacitive sensor, we think it's matching quite well. The question in terms of how much compression on the finger, in terms of exactly when the user is feeling that they've hit the screen, is a very difficult question, because it's an arbitrary threshold where you've tuned a given capacitive screen.
Well, that's the complexity, because your design, in some sense, is preload the capacitance, and then you trigger the capacitance to trigger the threshold. The human touch changes, but further, the firmware, touchscreen firmware, would actually have to deal with that and factor in that as a variance as well as the environmental noise introduced to capacitance. So it can change in some ways, but it's still a good baseline, I would say.
Thank you.
Thanks.